Davey, let's talk about soil pH. Here we are, this beautiful site in Tenerife, studying soil science. It's always been known to me that soils, as they progress through soil formation through time, don't they acidify to some degree?
Mm-hmm.
Why is that? Can you explain what's going on there?
I mean, certainly during the pedogenic process, the formation of soils, you get, you have bare rock, for example, and then that starts to form soils. But if you get one of these rocks, so if we got this rock here and we ground it up and then we measured the pH of that, the pH of that would probably be about 7.4. So it's quite, it's on the alkaline side to start with, and then, as time progresses, gradually it breaks down and forms, secondary minerals and stuff. And gradually the pH of the system starts to drop. And I think, there's a number of reasons why that happens. One of it is, the rainfall, the pH of rainfall is about 5.5, so it's always dropping acid onto the soil every time it rains.
H+R is just coming in.
Exactly. The second reason is that the plants that we have around us here, they're all taking up base cations. They need calcium, sodium, potassium and magnesium.
Right.
And then every time they take cations out of the soil, well, they can be replaced by other cations that come off the rock, but ultimately, they run out and they get replaced with hydrogen ions, so the pH starts to drop because of that.
Right, again, yeah.
The plants are also, acidifying the soil, because generally that's a better way to get some nutrients that are quite difficult. So things like phosphorus, for example, in many soils, the plants will release acid through the proton pump the roots have, that releases hydrogen ions, continuously pumps them into the soil to lower the pH of the rhizosphere, and that also drives partly acidification. So and I guess probably over longer time scales, here we're talking millions of years, so the pH will gradually drop over time, and it sort of has an exponential drop with time. And it starts at about 7.4 and ultimately it reaches in a typical mineral soil about 4.5. So, and that is driven by many of the processes I've just discussed, but probably of critical importance really is the leaching. As you get water, when you have an excess of water in moving through the system, it's actually taking a lot of those nutrients out of the system, so you get this loss of the base cations, in particular the sodium, potassium, calcium and magnesium, and ultimately they get replaced with hydrogen ions. So
wow. So that explains why. Haven't I seen that in long-term studies of chronosequences where people have studied soils from around in the same place from sort of relatively young to thousands and thousands of years old, that explains why soil acidifies over time for exactly that sort of thing.
And I think if particularly it's particularly prevalent in the tropics.
Yeah.
Where soils are millions of years old, or in Australia.
Yeah.
And they're the pH is there around 4.5. So you start off with the inceptosols and the entosols at the start of soil formation, which have a high pH, and then gradually as you go through the mollisols, the alphasols, the andosols, for example, you're dropping into the 6s and 5s, and then as you start to weather out those soils, the oxasols and the ultrasols, they drop to about 4.5.
Wow. And
the exception is, the vertisols, which are somewhere, they're actually receiving a lot of the base cations that are lost from the other soils, so they retain actually a higher pH. They're benefiting from the loss from other soil systems.
So, okay, so that's the kind of great overview of the theory, if you like, of what's going on. So and that's in terms of natural systems. So let's think now about, the parts of the world where we've got productive soils, crops and agriculture and so on and so forth. They also acidify, don't they? Right. But for slightly different reasons.
Yeah,
can you explain that?
Some agricultural soils will acidify, at an incredible rate, depending on particularly the type of fertilizers we use. Mm-hmm. If you put an ammonium-based fertilizer on, for example, ammonium nitrate or urea, you think of the chemical formula of ammonium.
Loads of farmers do.
Yeah, it's very commonly used. And ammonium is NH4+.
Yeah.
And the microbes in the soil convert that to NO3- nitrate.
Yeah.
And the hydrogen ions on the ammonium have to go somewhere, and they go into the soil, and you have that acidification process.
Yeah.
And also you have a lot of nutrient stripping from the crop as well. So that is also driving, the pH to drop.
Yeah, just organic acids from the crops and so on. Yeah. So hence why the farmer might use lime or something to buffer against that.
Yeah, so you've got a couple of options really. But mostly people will apply calcium carbonate to buffer and raise the pH back. And really for optimal crop production, we're looking at pH 6 to 6.5 would be perfect. But many of the acid soils in the world, the oxasols and the ultasols, are pH 4.5. So, and you have to think, Phil, about pH is on a log scale, of course.
Yeah.
So when you go from pH 7 to 6 to 5 to 4 to 3, for example, you can get to 3 in some of the organic histosols because they're not buffered so well. That is going 7 to 6 to 5 is 10 times more acidic, 100 times more acidic, 1,000 times more acidic, 10,000 times more acidic. And I think sometimes we forget that pH is the log scale.
So that's great, but I'm imagining people watching this, might be thinking, so what if pH is low?
Yeah.
What does it matter? What happens? Why does it matter? What's the consequence of a low pH?
I mean, I think it's a fascinating question, and some people often ask me that. You see an oxasol and ultasol in the tropics, and you look at the tropical rainforest and you say, but there's hundreds and thousands and tens of thousands of plants growing there. Why are we so worried about it? Because they're quite happy growing there. And I think all of those plants are super adapted to growing on acid soils, whereas the food crops that we mainly grow, most of them came from the Middle East, which is calcareous soils predominantly, so they're not designed for surviving on the acid soil conditions. So, and the key thing is in an acid soil, as the pH drops to pH 4.5, it reaches that critical limit at which aluminium suddenly becomes toxic.
Right.
So aluminium is released into solution at pH 4.5. Until that point, it's held as aluminium hydroxide or in clays and things. When you hit pH 4.5, and suddenly it solubilizes almost instantaneously like crazy.
Yeah.
The aluminium 3+ comes in to the soil solution. It then hits the roots of the plants, and essentially the roots develop Alzheimer's disease. They can't remember what they're meant to do, and it interferes with membrane transport, it interferes with growth, and basically without your root system or your mycorrhizal friends, symbiosis, you can't survive. So that's the critical thing about pH. It's the aluminium effect.
Okay, and so aluminium overriding, but of course all the other nutrients, elements in the soil will also be affected by the acidification as well. But aluminium is the key one.
Yeah, and of course, as the aluminium becomes soluble at pH 4.5, it then comes into solution like crazy. It then knocks off all of the base cations in the soil, which then leach out. So you're basically driving this sort of, it towards a nutrient-poor system.
Nice one.